Welcome. After learning some balance equations and how to set up the balance equations to analyze the various problems involving mass transfer, heat transfer, and momentum transfer, we should now learn some fundamentals about how to solve these balance equations. And these balance equations, as you can see, involve some kind of differential, and when you set up the balance equations for using some kind of finite difference technique, you will find that you will end up with some set of equations which are generally linear. If they are not linear, you sometimes linearize them, because linearized equations are much easier to solve than the nonlinear equations. And in all these things, you find that you have different forms of the equations, and sometimes you need to also interpolate something in between, sometimes extrapolate. So there are various mathematical techniques also involved, and to give it a complete shape, in the next few lectures, we shall be looking into some of the fundamentals of the mathematical and numerical techniques we use to solve the model equations. So I shall be starting now with some metric techniques which we often use in solving these model equations. So I shall be restricting myself only to the common ones, and it will not be an exhaustive exposition on the matrix techniques to solve the various types of equations. So in this particular lecture, we shall be looking to two of the methods. One is the LU-decomp and another is the tridiagonal matrix algorithm. So first, let us see that what kind of equations we are targeting to solve. So here we have a set of linear or linearized algebraic equations. Now it means that you can see that from the form of equation, all the terms are linear. There is no square or cube or square root or anything. Okay, so that is how you are getting the linear equation. And suppose you when I say linearized equation, it means that if the parent equation is non-linear, and what you do, using say Taylor series, we linearize them. For example, you take that y equal to x, you take this is a linear equation. Okay, this is a linear equation. So there is no problem with this. But suppose y is equal to x square. In that case, what you do, that you linearize this equation like this, that you take the Taylor series. From that you find that y equal to, say we say x plus delta x. Okay, so we take that y at x plus delta x into dy by dx at x, and we are neglecting the higher order terms. With the order will be, this is the higher terms. Okay, now you see that in this case that when we neglect these terms, we find that we get this dy by dx will give you 2x. Okay, so that is how we are able to linearize the given set of equations. Okay, so now you see that if you put all these equations, and we shall see some examples later on that how we can get such kind of equations. We see that here we can write these equations in these terms. We put a11, a12 because we are try to put in a matrix form. So we put a11, a12 up to a1n, and we have x1 to xn number of variables. Then we have x2, a21, x1, a2 to x2 like this, a2n to xn, and this b2, and then we have an1, x1 to an2, x2 to ann, xn, bn. Okay, so now you see that with this we can put all this system, club these systems into a matrix form, and we put this a matrix, then x is the vector of the unknowns and b is some kind of forcing function, we say. So a is represented like this, that here we have a11 to a1n, it will be a small correction over here, it will be a1n. Okay, and then similarly a12 to a2n, and then we have this an1 to ann, and then this x is the vector, this x1 to xn, and b is another vector, this is b1 to bn. So this is how we set up the model equations. And after we have set up this model equation, you see that this here we have to solve for x. Okay, and generally if the order of the matrix A is small, we can take the inverse of A easily and we can solve for x. But as the dimension of A becomes more and larger, then it is not possible to go with the inverse, because that will prove very inefficient. So generally we take some help of some other techniques to solve for x, and we shall be looking into those techniques. So you see that there will be some direct methods and then indirect methods. Direct methods means at one go. For example, if you are able to take the inverse of A, then you will get the value of x at one go. Okay, so that is a direct technique. And if you are not able to take the inverse of A, then what you do some iterative technique, okay, to solve for x. So both these techniques are there, and most of the times we go for the iterative techniques because the dimension of A is very large. So first let us go with one of the common methods, that is the LU decomposition method, or in short we call it LU decomp method. And LU means that we resolve the parent matrix into two matrices. One is the lower triangular matrix and that is the upper triangular matrix. Perhaps by triangular matrix you know that if we have the one half, if you have a matrix and you along the diagonal, say upper half is filled up and lower half is having all zeros, then we have a upper triangular matrix. On the other hand, below, if you have below the diagonal elements, we have the non-zero values, most of them are non-zero values, and upper elements are all zeros, then we have a lower triangular matrix. Okay, so in that fashion we resolve this parent equation into two matrices, that is lower triangular and upper triangular matrices. And you can see that you can find, this is one of the ways, you can see that for the lower triangular matrix we are having all these elements L11, L21, L22 and other things. The above the diagonal all the values are 0. On the other hand, for the upper triangular matrix we are considering these diagonal elements to be 1 and rest of them are not necessarily unity, they may or may not be unity, and but the below this diagonal they will always be 0. Okay. Now you can see that if you multiply these L and U matrices by comparison with the parent matrix, you can find the value of all these elements of the lower triangular and upper triangular matrices. So here I have shown you that if you consider row 1, you can get the value of L11, U12, U13, etc. Then if you go to row 2, you can go to L21, L22, L23, etc. So this is the way you can keep going on and you can find all the values of these L and U. Now once you have got the values of L and U, what you do, that you know that you define that ux to be say another thing y. Okay. Now what you do, that you want the value of x. Okay. So first you solve for, that means you are getting Ly equal to b. Okay. So from this lower triangular and this b vector, you can find the value of y very easily, because you can set this equation like it will be lower triangular matrix and this will be y1, y2 up to yn. Okay, and into this b1, b2, etc. So you can see easily, you can find out that if you go forward swap, you can find the value of y1 will be equal to b1 by L11. Okay. So similarly you can make a forward swap. So you get all the values of y. Once you get all the values of y, now you put the value of y here. Now you have a upper triangular matrix here. Now what you can do, now you can do a backward swap. So that means you will now find xn, xn minus 1, xn minus 2 and you will go to x1. Okay. So that means in the two steps you are able to get this value of the x. Okay. So this is a very handy method. So you can see that even if B has changed, okay, and your A matrix remains the same, you do not need to do anything. if you actually all these methods come from the naive Gauss elimination method, in which you work with all the elements, and if there is any change on the right hand side, then you find that you again have to redo the whole problem with all the elements. Okay, but in this case we are able to circumvent that kind of problem. So this L and U will remain the same. Only thing is this: if B changes, Y value will change, and Y value changes, that means X value will change. So in case of Y, you go from Y1, Y2, Y2, Y3 up to Yn, and in case of X, you go from Xn, Xn1, Xn minus 2 to X1. Okay. So now this is not the only way to resolve A. You can have another way of resolution of A. That means I can put the L and U like this. That in this case, for the L matrix, I put all the diagonals as 1, and for the U matrix, I put all these diagonal elements as not necessarily 1. Okay. Now again you find that by comparison of these multiplication of these two matrices with these individual elements, you can again find the value of U and L. Okay. So with this thing, again the same methodology, that you first find this LU, again find the value of the Y, that is UX, and then from that you find the value of X. Okay. Now we take this example problem. So this is the A matrix given to us, and this is how we are going to now find out that how we are going to decompose this A matrix in a L and U matrices with the Kraut's method. And here I have shown you that how you can get the values of all the elements of this lower triangular and the upper triangular matrices. Okay. So you can go one by one. You can see first we get this L11 as 3, that is this one value, then L11 U12 is equal to 2, okay, that is this, and this way you keep on. First you take this particular row, then you take this particular row, and you take this particular row, and you solve alternately for L and U, and you can get all the elements of L and U. So here you have the lower triangular matrix and the upper triangular matrix. Okay. So it is here we have the basic thing is this: we have learnt how to decompose the matrix into L and U matrices. Now once you have got this, I can give you any other function that will be the B, okay, forcing function, and now you can solve for the X. Now before we go to another kind of solution, here is a special kind of solution that many times we find that we deal with sparse matrices. Sparse matrix means that most of the elements are 0 in the matrix. So for the efficiency of the computer coding, we do not need to store the 0 matrices, and many times we find in our transport phenomena problem, we have only in a given equation, we do not have all x1, x2, x3, x4 up to xn in a given equation. We have only neighboring points. That means suppose I talk of a point I, where and these equations are obtained from the finite difference equations generally. So we find, suppose I talk of a point I. Suppose I talk of a point I, and on the right hand side I can say I plus 1. And left hand side I am doing a one dimensional problem, okay, one dimensional problem. So suppose what I, with respect to I, we have a I plus 1th point and I minus 1th point. Suppose we are talking temperature, I want to find the temperature gradient, suppose, okay, and suppose this is the x direction. So I have Ti, then Ti plus 1, and then Ti minus 1. Similarly, if I want to find the velocity profile, I will have Vi, then Vi plus 1, and then Vi minus 1. Okay. So and so forth. Similarly, you can go for the species concentration. So when you set up this kind of equations in the transport phenomena, you find that you get an equation which will look something like this. That suppose you have Ei, sorry, xi minus 1 plus fi xi gi xi plus I plus I plus 1 is equal to some Ri. Okay. So, these are typical equation you get, and you see that in this equation you are not having the values at all the points, you are having only the boundary points here. So, when you write this kind of equation for whole system, you find that you get a system of matrices which will look like this, that you will get this on the F1, then F2 up to say Fn. Okay. Now I goes from 1 to n, and on this side you will have E2, on this side you have G1. Okay. Then you have 0 here, then E3, F3, then G3. So you will find that most of these things will be 0, and you will have 3 bands. One is G2 here, G3 here, like this it will go. So you have a banded structure. So one is the main diagonal, then one is the super diagonal, and one is the sub diagonal. So only these 3 things will be there with you, and rest of the elements will be 0. So in this case it is not an efficient technique if we are going to use the naive Gauss elimination. So in this case we have some particular techniques which are only for this kind of situations, and because now we have 3 diagonal, one main diagonal, one sub diagonal, one super diagonal, we call it a banded structure. Band. So we call this, there are 3 things are there, so we call it tridiagonal matrix. So it is not that we have only tridiagonal, we can have pentadiagonal also. We can have 2 subdiagonal, 2 super diagonal. So various situations may be there, which will, depending on that, we will having this kind of banded structure. And for any kind of banded structure, the naive Gauss elimination method can be modified so that we do not have to deal with these zeros. So in this particular figure you can see that we have the bandwidth, the total number of the rows, these columns is showing the bandwidth from the sub diagonal to the super diagonal. Okay, and half diagonal is the from the diagonal element say to up to the say super diagonal or the sub diagonal, you call the half bandwidth, and rest of the things, these particular things show they are 0. So rest of these elements are all zeros. So in this particular lecture we shall be looking into only the tridiagonal matrix systems. Okay. So here as I have shown you that this is the tridiagonal matrix system. Here you have the main diagonal, this is the super diagonal, and this is the sub diagonal elements, and here we have all the unknowns to be solved for, and here we have the all the forcing functions. Now these can be done, these can be solved by 2 ways. One is that we can modify the Gauss elimination method, and another is the we can use the LU decomposition method. Now if I go, let us go one by one, that if you go with the modified Gauss elimination method, then we will be reducing our system into this form. It is something like an upper triangular matrix with all the diagonal elements as 1, and we shall be having only one super diagonal. Okay? That means half bandwidth is 1. And you see that we are putting this prime because when we are converting the parent equation in this form, all these values are getting changed, and these values have been given like this here. You can see that you can find this G1 prime, G2 prime, G3 prime for this from this formula. Okay. So once you get all these G1 prime, G2 prime, R1 prime, R2 prime, etc., then you can now solve for this x. Now in this case you can see that you will go swap backward. Now why? Because the xn will be equal to Rn prime. Okay. Once you get Rn prime, then you see that from this what you get from this one, you get xn minus 1 plus g prime n minus 1 into xn equal to Rm R prime n1 minus. So you know xn, so you can find the xn minus 1. So next when you go to xn minus 2, it will involve xn minus 1. Then you, as you move up, you will find that with x2 will be involving x3, x1 will be involving x2. So that is how you are going to backward sweeping you are doing to get the values of all the x. So this is based on the modified Gauss elimination. Now we go for the LU decomposition. In LU decomposition, again you can see that this is the way you can go for the LU decomposition, and here we have demonstrated with a example problem that how you can get the LU decomposition method to obtain the solution for a tridiagonal matrix system. So here you can see that as you apply the LU decomposition algorithm, you find that at each step you are able to get how the values are getting modified, and ultimately you are getting these two matrices. In this is the L matrix and this is the U matrix. Okay. So you can see that in the L matrix, this is something following the Kraut method. You see that all these diagonal elements are 1 and you have only half bandwidth, that is 1. And in this case of U matrix, you can see these are the diagonal elements and these are the super diagonal elements. Now these are the R, that means as you are going for you are changing the L and U, you know that you have to also change the R values. So this is how you are getting the R values, and here you are solving for the T. As I told you, you go with a backward sweep you go. So you are getting the value of the Tn first. So then you get the value of the Tn minus 1, then you go to n minus 2, and then ultimately you reach the value of n minus. That means this is a T4, then T3, then T2 and T1. Okay. So this is the way you can see that once you have resolved the particular equation into the L and U, you are able to solve for these two. Okay. Now these are the books which you can refer to for more examples and illustrations and explanations of these techniques. Thank you.